All right, welcome to chapter 3 or video 3.1. We're going to talk about balancing chemical reactions. And I want to start by showing you a YouTube video of a demo that I typically do in class where I burn steel wool in air. So many of you have seen steel wool. It's this abrasive stuff that you use to, say, strip paint off of a metal object. What happens though if you've got some steel wool, so let's just draw it up, it looks like this. This is exactly what it looks like. So here's your steel wool, and let's hit it with some flame, and we burn that stuff, right? And let's assume that before we burn it, we're going to put it on one of these top loading balances, and then we're going to read it out to some maybe 4 significant digits of its mass. Let's do that. Let's burn it, and then let's see, we'll say the burn stuff is green. It's not really green. And let's do that again. So let's throw it back on the same balance, which again, I would do this in front of you if you were here, but you're not. So we'll watch a video. What's your prediction here? If we've got steel wool, which I'll just tell you is iron, or Fe, and I hit that with some high temperature, and I burn it and actually combust it, what do we expect these two things to do? Do we expect these two masses before and after to be the same or different? So think about that for a couple seconds. Pause the video maybe, and then start it again and we'll watch the video. Okay, so we've got the YouTube video here queued up. So in the center, we've got some of this steel wool. Somebody with a gloved hand is going to put it in the center. Typically, you hit this with a propane torch to get it started burning. They're not going to show the torch, but they'll show it incinerating. So this is what it looks like. It's this beautiful effect. Once it starts incinerating, it'll start to burn. It's easier if you sort of spread it out a little bit. Oh, there's the torch. So you can start it burning, and then it'll persist on its own for usually several minutes. So let's let that occur for a couple seconds. Let's see, maybe we can speed this up a little bit. It's almost done, and we'll call that done. Okay, so let's think about then what this actually means in the context of this experiment. What's our possible reaction? So I think maybe your intuition, especially on the heels of maybe just watching the law of conservation of matter, you might be compelled to think that I'm asking you a trick question and they're actually the same. But that's not true. What's actually happening is, well, what happens when you burn something? Well, we've got iron that we start with, that's the steel wool, and the burning process is it reacting with oxygen and air. And the burning part is just the heat to get this reaction started. And so if you have iron and oxygen, what do you think they create? Well, they create this stuff called Fe2O3, which we talked about in a previous video. The name for this stuff, you all know, is rust. So essentially this is just a really, really fast rusting process. So what's our thought here then? If we know this to be true, if this is what's actually happening when you burn steel wool, is the mass the same or different? Well, think about that for a second. So we start with pure iron, that's the steel wool here, right? And now we end up with something that's no longer pure iron, but it's iron attached to some oxygen atoms. Do oxygen have mass? Absolutely they do. And so this new stuff will absolutely be heavier than what we started with because it now contains some oxygen. But we need some tools here to make sure that we can actually compute this, right? We should mathematically be able to say, okay, we started with 4.23 grams of iron. If I burn all of the iron in an infinite amount of oxygen just in our atmosphere, what will the mass of this thing be? We don't have those tools yet. And the first tool that we're going to need to use is the balancing of chemical reactions. And so when we're balancing a chemical reaction, we want everything on the reactant side, we want the number of atoms on the reactant side to equal the number of atoms on the product side. They have to be true. And that's based on the law of conservation of matter that we'd already talked about, right? We can't create or destroy iron atoms. That's transmutation, that's alchemy. We can only convert them from one form to the other. And the same goes with oxygen. So these two things have to be equal. If we look at the reaction right now, this rusting reaction, it's not balanced. We've got one iron atom here, but we've got two in this rust compound. We've got two oxygen atoms here, but we've got three over here. And so we need to use coefficients to make sure this is balanced. And so let's use the rainbow color here. So for coefficients, we'll come in and I'll walk you through how to do this. We'll have 4 irons here, and we'll have 3 oxygens here, and we will add a 2 in front of this. And that will give us a total of 2 times 2 irons. That gives us 4 irons, which is the same as what we have here. That gives us 2 times 3 oxygens, which gives us the same as 3 times 2, or 6 on both sides. In this case, this is a total balanced chemical reaction where the number of reactant atoms is exactly equal to the number of product atoms. And this is the first step in being able to answer this question, which is, well, if we know how many grams we started with and we know they react in this proportionality, then how much do we have at the end? That's what we need to get through by the end of chapter 3 here. Okay, so let's walk through a step-by-step process for balancing chemical reactions. It's pretty straightforward once you sort of memorize the process by which we do this, and you apply it to any reaction. So the first step is pretty obvious. We just need to write the full reaction in the unbalanced form. And so we're going to use this as the example where we have NH3, which, just so that you know, is ammonia plus oxygen gas makes nitrous oxide plus water. So that's the very first step. Okay, step 2, now we want to use coefficients in front of these individual, what we call formula units. I'm going to call these formula units because these are the simplest chemical formulas to represent those individual compounds. What we don't want to do, which I alluded to earlier, is we don't want to add numbers like this, which would change the chemical identity of that particular species, right? We want to put numbers only in front of these to signify that we're changing the whole number of those formula units. So don't change the number such that the formula unit changes. Those need to remain the same, which is meant here. Formula units can't change. Okay, so we need to use coefficients, but how do we do this? Well, the sort of first rule of thumb is to start with elements that only appear in 2 separate species. So let's look at all of these things and let's identify elements that only show up in 2 individual formula units. And so it looks like, for example, hydrogen appears only in 2 species. So we've got hydrogen here, and we've got a hydrogen in here, but we have no hydrogen in the oxygen, and we have no hydrogen in this NO. So hydrogen appears in NH3 and the H2O, and also nitrogen only appears in the ammonia and the NO. So we've got 2 candidates here for this first rule. So nitrogen is in the NH3 and the NO. So only in 2. So let's balance these first. So let's write out the NH3 plus O2 makes NO plus H2O. And let's balance the hydrogen first. Let's do that in red. So we've got 3 on this side and we've got 2 on this side. And so the sort of common multiple here would be 6. So if I multiply this side by 2, that gives me 6 hydrogens. That would mean I'd multiply this side by 3 to get the equivalent 6 hydrogens. And so at this step, we have hydrogen balanced. Not all the other stuff is balanced, but hydrogen is. Okay, So now let's do nitrogen. So we've got the 2NH3 plus O2 makes NO plus 3H2O again. And let's do nitrogen in blue in this case. We've got 2 nitrogens here, only 1 here. This is an easy one. We just need to take this common multiple of 2, pop that there, and now we have nitrogen balanced on this case. Okay, so that is the second step, using coefficients to balance by starting with elements that only appear in 2 different species. Okay, so we want to finish here, at least in step 2, by balancing any solo elements that exist by themselves. And so you can identify solo elements as those that exist in a formula unit with no other element. And so in that case, it's pretty clear that the only version of that we have is O2, because it's not bound with anything else. So the convenience of this and why we do it last is because we can change this and it doesn't change anything else because it's not bound to anything else. We can change this number on this side without changing the number of another element simultaneously. So if we look at this side, let's see, we've got 1 oxygen here, but times 2, so there's 2 oxygens, and then we've got 3 oxygens. So we've got a total of 5 oxygens on this side. We have 2 on this side, so we need a common multiple here. We can do this fractionally because it's pretty easy to do it that way. We can multiply this by 5 over 2. Multiplying this by 5 over 2 would give us 5 oxygen atoms on this side and 5 oxygen atoms on this side. So that would be a really simple way that doesn't make us multiply all of these other numbers out as well. Okay, final step then is we don't want to leave our balanced chemical equation with these fractions, even though that was convenient for us. We want to report these coefficients to the smallest whole number. And so that's pretty simple to do here. We can multiply this whole chemical equation by 2, and that's going to give us this new balanced chemical equation of 4 ammonias plus 5 O2s makes 4 NOs plus 6 H2Os. So this would be the smallest whole number coefficient representation of our fully balanced chemical reaction. And that series of steps is going to work for virtually all, at least general chemical balance. Okay, let's do one quick example, maybe on your own. So let's take this example here, which is propane gas. So this is the stuff you'd use on like a barbecue, which has a chemical formula of C3H8. I don't have the ability to have subscripts here, so you can write it like this. That combusts with oxygen gas, which looks like that, to yield carbon dioxide and water. So this is asking us to know what carbon dioxide is, so that follows on the nomenclature that we'd used before. And so let's break this down into steps. I want you to pause the video here and see if you can break this out, and then unpause it when you're ready to walk through this step by step. Okay, first step is to write the full unbalanced reaction. So that's just taking these compounds, knowing which ones are reactants, which ones are products based on the phrasing of the question. So we've got propane here plus oxygen gas makes CO2 plus water. This is the fully unbalanced reaction that we're starting with. Okay, second step is we want to balance those elements that appear in 2 different species. And so we can look back at our balanced reaction. We can identify that carbon only appears in the propane and the CO2, so that's one option. And then hydrogen also shows up in propane, but then in water. And so those are going to be the 2 things that we want to balance first. So if we want to balance carbon first, we can see that we've got 3 carbons over here. In the CO2 side, we've only got 1, so we multiply that by 3, and now we have carbon balanced. Okay, let's do the same thing for hydrogen. And so we look over here and we see that there are 8 hydrogens in the propane. There were only 2 to start with in water, so common multiple would be 8. We multiply this whole water unit by 4. That gives us 8 hydrogens, 8 hydrogens. Now we've got both carbon and hydrogen balanced in this version of the reaction. Okay, last step here then is to balance the solo element. In this case, same as last time. We've got oxygen that exists by itself. It's not bound to anything, so that's the sort of last knob that we can turn. That doesn't change anything else. That's why we want to do it last. So we look and count the oxygens on this side first. So we've got 3 times 2 gives us 6 oxygen coming from CO2. So there's 6 O's there. And then we have 4 oxygens coming from water, which means we have a total of 10 oxygens on the product side. We've got 2 for every oxygen molecule. The multiple is 10, so we multiply this whole thing by 5. That gives us 10, which is equivalent on both sides. And now we've got carbon, hydrogen, and oxygen all balanced. That turns out to be the only elements actually in our entire balanced chemical reaction. So the last step, step 3 here, would be to reduce everything to the smallest multiples, and in this case we have a 1, a 5, a 3, and a 4. They're already at the smallest representations they can be, and so this is our final balanced reaction. So practice these on your the workshop, the handout, and at the end of the book, because it's not that challenging, but it does take a little bit of practice to recognize the sequence of events here.